Hello everyone. Myself Priyanku Ranjan from Chemical Engineering Department, and I'll be sharing my in-depth exploration of a foundational concept in the world of finance, which is the Black-Scholes model. This model, crafted by Fisher Black, Marvin Scholes, and Robert Mason, has left an indelible mark on the field of option pricing and revolutionized the way we perceive and analyze financial derivatives. Imagine the complexity of the financial markets, where myriad factors converge to determine the value of options. Black-Scholes model emerged as a beacon of clarity, providing a structured framework to estimate the fair value of European-style options with astonishing accuracy. Its brilliance lies in simplifying the intricate interplay of variables into a coherent equation. At its core, the Black-Scholes model considers five critical components, which is the current stock price, the option strike price, the risk-free interest rate, the time to expiration, and the volatility of the stock price. These elements weave together to unveil the option's theoretical price, offering profound insights into market dynamics. The beauty of the model lies in its ability to provide a true approximation of option price, even in the presence of market complexity. However, it's important to acknowledge the model's assumptions. The Black-Scholes model assumes constant risk-free interest rate, continuous price movement, no transaction costs, and a constant volatility. Apart from this, I also worked upon how the option prices are changing. Like suppose the Nifty 50 index goes up by 50 points, then what will be the change in the price of the options? And I found it very closely associated with the previous strike price, which was very interesting. Yet, the real world is a tapestry of intricacies where markets ebb and flow with unpredictable events. As a result, the Black-Scholes model may fall short in certain scenarios. Nevertheless, it serves as a foundation upon which more sophisticated models have been built to account for this real-world complexity. In conclusion, my journey into the depths of Black-Scholes model has revealed its power, unveiled the hidden values of options, illuminating the path for investors and analysts alike. It has laid the groundwork for a new era in finance, shaping our understanding of risk and return, and facilitating better decision making in the dynamic world of credit. Thank you all.
Uh, Hello, myself Abhay. Today, I will be sharing with you fascinating journey that has taken me into the intricate realm of financial derivatives, where I have immersed myself in understanding the nuanced differences between Asian and American options. Through extensive research and empirical exploration, I have delved into the depths of these two types of options, unraveling their unique characteristics and shedding light on their practical application. Asian options and American options are both compelling instruments that provide investors with distinct ways to manage risks and potential rewards. Asian options, sometimes referred to as average options, differ from their American counterparts primarily in how they are exercised. Asian options are settled based on the average price of the underlying asset over a specific period, while American options can be exercised at any time and including the expiration date. In my meticulous study, I not only comprehensively grasped the theoretical foundation of both Asian and American options, but also ventured into the world of empirical research. By analyzing real world market data, I sought to uncover the practical implication of these options in various market conditions. This empirical exploration provided invaluable insight into how these options perform and behave under different scenarios. Through meticulous data analysis, I observed that Asian options tend to exhibit unique characteristics compared to their American counterparts. The reliance on average prices introduces a smoothing effect that can mitigate the impact of short-term price fluctuation, potentially making Asian options more attractive in certain market environments. On the other hand, American options offer great flexibility due to their ability to be exercised at any time, giving investors more strategic choices. This research journey has led to me appreciate the delicate balance between theory and practice in the world of finance. While theoretical models provide a solid framework, empirical research breathes life into these models by grounding them in the realities of market dynamics. It's the empirical exploration that we witness, the convergence of financial theory and practical decision making. In conclusion, my venture into the realm of Asian and American options has been a transformative experience. It has equipped me with a deeper understanding of financial derivatives and insight to make informed investment decisions. I am honored to share this journey with you today and am eager to engage in discussion that further enrich our collective understanding of these fantastic financial instruments. Thank you.
Here is a Python script that assesses the accuracy of the Black-Scholes model by comparing its calculated option prices to the real option prices derived from the Nifty 50 index options. Here we are using NumPy and Norm library. So let me first tell you the variables that I am currently using. I store the choice of user. He may input 1 to calculate the call option price or 2 to calculate the put option price. S stores the current Nifty 50 index, which was 19,265, which was at 25th of August. K stores the strike price. R stores the risk-free interest rate, which is currently at 10%. Sigma stores the implied volatility in percent. T stores the time for expiration in years from 25th to 31st of August, which is total of 6 days upon 365. Depending upon the user, it will calculate the call option price for Black-Scholes model or put option price. This is the function which it will call. To calculate the call option price, we need to first calculate D1 and D2, which is as follows, and it will return based on the D1 and D2. So and similarly for put option price, there is a slight change in the formula to calculate the put option price. On the right side of our screen, we can see the Nifty 50 option chain. The C column has all the strike option. The A column has all the implied volatility for call option, and similarly, E has implied volatility for put option. So now I will demonstrate you how the code works. So we will calculate for call option price. So we have to enter 1. Currently, the Nifty 50 index is at 19,265.80. We want I want to calculate the strike price for 19,300, which have a current interest rate at 10%, so 0.10, and for 19,300 we have a sigma at 6.42, and for 6 days it will be 0.0164. So we can see the result is very similar to the actual price. Actual price is at 62.05 and we got calculated at 61.91. So now we will do this for all the strike prices. So this is the main program that we will run for all the strike prices. Here we are using pandas library to extract all the data from the Excel. So if I want to take all the strike option price, first I need to have create an array, and this array is being created from the array library, and we will take all the strike price using the log function in the pandas, and we will store them into value 1. And since the value 1 is actually a string, we need to first convert into integer, and we will store that into data strike. And similarly, we will do that for iv call, iv put, iv ltp call, ltp put. I have already entered the srt value, which is fixed. K will store the data strike price from the strike column and from the array that we created earlier. And similarly, real price call, real price put for the put price, sigma put, and the model price call will store after Black-Scholes call will be called. And the percentage error call will calculate the percentage error between model price call and real price call. And similarly, percentage error put will calculate the error in model price put and real price put. And at last, we will print the real price call, model price call, percentage error call, real price put, model price put, and percentage error put. Now I will demonstrate you how this code works. So as we can see that for strike price of 19,200, we have a real price at 108.60, but the model price is 108.50, which is nearly close to 0. And the percentage error is negative of 0.09%. And if we calculate the same for the put option price, the real price is 85.95, but the model price gave us 85.32, which has also the relative percentage error is negative of 0.73%. And we can see that nearly in all the values, the percentage error haven't been gone more than 2%.